So today we'll talk about the SN1, E1, SN2, E2. So um, up until now, what you've really looked at has just been the fundamentals and foundations of organic, meaning you had to understand the wordplay and nomenclature of how do we name molecules, how do they exist in 3D space, how do they orient themselves. Um, And the reason for that is that it tells you so much about reactivity. And it's easy if I say, hey, Mag, here's this molecule 2S, 2-bromobutane. You can draw that molecule out because it's a common name. Now that that's all under your belt, you are still learning nomenclature for functional groups as we go through, but most of what you're doing now is just the reaction chemistry, the important aspect of organic. And all it boils down to is if I give you A and B, you should be able to tell me what product is going to form, or if no product will form at all. And that's really at the heart of what's happening in this part. And so all we want to do then is just really focus on the basic stuff so that if you understand the basic terminology, everything else is just going to fall into place. So I'm going to share screen and I'm just going to whiteboard this just because I think it'll make a lot more sense if I just write stuff down. So in our basic idea of what is happening, we have 4 reactions: SN1, SN2, E1, and E2. So the way to think about this is that these reactions are similar and these reactions are similar. They're both, this is SN1. The S stands for substitution. So you are essentially replacing something with something else. And you're doing it with the N part, which is nucleophile. It's a nucleophilic substitution. The 1 or the 2 tells you how many things are involved. Is it one thing at a time or is it 2 things at once? So we'll go through and highlight that a little bit more.
Isn't SN1 just one thing
One at
happening?
a time. Yep. And that's how you should think of the numbers is one thing involved or 2 things involved. And with the E reactions, these are elimination. You are removing something and a hydrogen. So in substitution, you are replacing something, right? So some type of leaving group is becoming something else. And in elimination, you're losing the leaving group plus a hydrogen. And you're always forming a double bond. And again, it's always going to be 1 or 2 things that are happening. It's going to be 1 thing involved or 2 things involved. And those numbers are still there. But here is the quote unquote fun part. And I say fun part, but I know it's not true. These are very similar and these are very similar. They're going to be a little bit of thinking of when you think of SN1 and E1, they can happen at the same time. SN1 and E1 are always in competition with each other. SN2 and E2, they can happen at the same time, but only in specific circumstances. And we'll go through all of those to make sure that you understand that. How are you so far?
Pretty good.
Okay. So let's start with SN2 because SN2, I think, is the best one to start with because you cover a lot of terms. And I think it's also the easiest to see and to really understand what's happening. So as we said, the S stands for substitution and the N stands for nucleophile. So our most common type of nucleophile, what you are going to most often see and what Dr. Dewis has shown you is something called an alkyl halide. Now, an alkyl halide is just an alkane functional group with a halogen. So you're going to have some type of alkyl group with the halogen. Now, there are 2 very important things that you should always keep in mind. 1, when you are talking about alkyl groups, something like this, right? And so say we're going to say bromine. Your carbon that you're doing these reactions must be sp3 hybridization. So if you see like a benzene with the halogen on there, or a double bond with the halogen on there, or a triple bond with the halogen on there, you cannot do SN2, SN1, E2, E1 reactions. It has to be an sp3 carbon. So it just has to be a regular old carbon that's attached to 4 things. No double bonds, no triple bonds, nothing. That is the one thing that you keep in mind, because a very common problem that professors like to give students is they'll give them something like this and say, I have this benzene with the halogen on here, like chlorine, and then they show you SN2 conditions, and they'll say, what's the product? And most kids will say, oh, it's an SN2 reaction, but it won't work. You'll learn about this chemistry later, so you would just write something like no reaction, and we'll go over that more specifically. But that is the most important thing to remember right now, is that your carbon has to be sp3. If it's not, then these SN and E reactions are not going to work. So we have our alkyl halide, and now I'm going to draw a sample, and we are going to label everything, meaning we're going to label every part of our reaction so that you understand the terminology. I'm surprised no one else is here.
I know.
Well, you get one-on-one attention today, and that's probably good for you, though, right?
Yeah.
Okay, so I'm going to circle some things in different colors, and then we'll go through and we're going to define each of them. I can hear a fire truck.
I can hear it too.
Sorry, hopefully it's not too loud.
No, it's okay.
Okay, so I have 4 things here colored different colors. So the reason why is that we want to make sure that all of your terminology is correct. So again, what type of reaction did we say we were doing? We said we were doing an SN, helps if I turn on the SN2, right? SN2 reaction, all right? So we're doing a nucleophilic substitution. So when you see these reactions, and as you get better at seeing them, you're gonna, I know you're gonna get this down, and it's gonna be like, oh, this is an SN2 reaction. This happens. This happens. This happens. So the simplest idea in a substitution reaction is that something, in this case, a nucleophile, is going to replace my leaving group. Meaning, I'm going to simply substitute my leaving group for my nucleophile. So you may be saying, well, what's a nucleophile? I'm sure you've covered this in class, so you probably know what a nucleophile is. But if you're new to this and you're saying, what's a nucleophile? What's a leaving group? This is the important part right here, is that we want to label all of these terms. So a leaving group is something, a leaving group is stable when it leaves. Because remember, in chemistry, we always care about stability. All right? A good leaving group is going to be very stable, meaning it's going to have a full octet. It could have a charge. Typically, the larger it is, the better. But it's stable when it leaves. And do you know what our best type of leaving group is? And this is why we're using them in our whole talk about the SNs and E reactions.
Isn't it water?
Water's good, but there's something a lot easier.
Oh,
halogens.
Iodine?
Yeah, well, iodine's a good one, but all of our halogens are pretty good leaving groups. Fluorine's not great, but we can make a leave. But halogens are really good as leaving groups. So in red is my leaving group. So whenever you are looking at this type of problem right now in this part of the book in tests, and you say, boy, I need to identify my leaving group, a good place to look is to look for a halogen right away. That's typically just a dead giveaway. Okay, so now we want to define what our halogen is attached to. So in the purple box, we have something called a substrate. A substrate is essentially what has your leaving group. And for SN2 reactions, it's what has our electrophile. And we will get a little bit more into electrophile in a couple of seconds. As I say hello to Melissa, good day to you.
Hi, how are you?
Good, how are you doing? It's nice to see you as well.
Good to see you.
I will also comment that Mag looked very happy and he looked very happy today as well. That's nice to see.
Thank you.
And hopefully you guys are happy. I hope that you're having wonderful days and wonderful weeks. So our substrate is everything in that purple box. It has our leaving group. It has our electrophile. It's everything there. That is our substrate. And the substrate is where the chemistry is going to happen in these reactions. So when we think about like, where is the substitution going to take place? Where is the elimination going to take place? Always on the substrate. Does that make sense? Okay. So now we have defined substrate and we have this defined leaving group. So the next thing we want to do is that we want to define our electrophile and nucleophile. So the important thing is that we are going to use a little bit of Latin because I know you guys just love Latin. But do you guys know what phile means? P-H-I-L-E, what the root word of phile is?
Lover? Is it
Yep.
like you love something?
Yep. So any type of, we typically use it in very bad connotations, but we're going to have two examples here. So our first one is going to be nucleophile. And again, helps if I turn on the writing. Nucleophile. And the other one is going to be the electrophile. So if I was to ask Melissa, what do electrophiles love?
Electrons?
Yep, they love electrons because they are electron poor. Meaning that the electron density is being pulled away from my electrophile. And typically, what element are we going to say is an electrophile? This being organic chemistry.
Carbon?
Carbon. Carbon is more often than not our electrophile, particularly at this level of organic chemistry. So electrophiles love electrons. They are electron poor. They are going to be attached to what? Looking at my image here.
The halogen?
What's the halogen more specifically?
The bromine?
More general. Leaving group.
Leaving group, yeah.
Okay, yep. So they're attached to the leaving group. All right. So the electrophile is where new bonds are going to be broken, new bonds are going to be formed. That is the actual specific carbon site of those. Does that make sense?
Yes.
How's it going, Melissa?
Going.
Okay. So then the other thing that we want to talk about then is our nucleophile. So what does the nucleophile refer to when it says, what does the nucleophile love? This is a once you hear it, you're gonna be like, oh, that's so dumb because I know it because I'm so smart and I remember Gen Chem. Nucleo refers to the nucleus, and what happens to be in the nucleus since we were just talking about electrons?
Protons.
Protons, yep. Our nucleophile loves protons in the nucleus, right? It's looking for positive charges. They are electron rich. All right, so nucleophiles are electron rich. Electrophiles are electron poor. So if you remember when we were learning about mechanisms and we were going over the basic rules, what was the first rule that we went over about what has to attack in reactions? What's always doing the actual chemistry? What subatomic particle?
An electron source?
Electrons, right? Electrons are always doing the chemistry. So in this type of reaction, where is my reaction going to start? From the nucleophile or from the electrophile?
Nucleophile.
The nucleophile, because it's electron rich, right? And so what do you think is a dead giveaway if you're trying to determine what a nucleophile is in your reaction?
The electrons, like the lone pairs.
Lone pairs, yep, anything with a lone pair can be a nucleophile, but what's usually a good dead giveaway that's like, nope, that has to be my nucleophile?
Oh, the negative.
Yep, if you see a negative charge, you have one here, that's usually indicative that you're having a, that's going to be your nucleophile. Now you can have neutral nucleophiles, and we'll go over that a little bit later, but this is just the idea that this is a dead giveaway. I'm pretty sure you guys have covered this material to a good extent, right? So if you want me to speed up, I can, or I can keep going at this pace.
No, you're good.
Okay. So now, in a substitution reaction, like we said, we are substituting something for something else. So our nucleophile is going to replace our leaving group. All right. So whatever our leaving group is always going to be replaced by our nucleophile. So the reason why I did SN2 is that SN2, I think, is the easiest mechanism to see. So carbon is my electrophile. So what was the one rule that we always had to be careful about when we were doing carbon chemistry?
The octet rule?
The octet rule, right? We can never violate the octet rule with carbon. It's in the second period, so we can't add more electrons than 8 at a time. So our current carbon in the blue box currently has 4 bonds, therefore it is sharing a total of 8 electrons. So if I want to form a new bond, I have to break one. Now that can either happen independently, or it can happen, it can either happen one at a time, or it can happen in concert. But this being an SN2, it means both are going to be involved at the same time. So SN2 reaction is also known as something called a backside attack. Because which direction does my nucleophile attack from? Relative to the leaving group. Backside. I attack the opposite direction that my leaving group is. So since my bromine is going to the right, I'm going to attack on the left side. And all that happens here is that in an SN2 reaction, substitution, one of my lone pairs is going to attack like this, right here, at the back of this bond. Now, was it Mags or Melissa? I don't remember who said I can't violate the octet rule. In order for this to happen, at the same time that I start that attack and start forming that new bond, my leaving group has to leave like this. So this is in concert, and this is where the 2 comes from. Both the nucleophile and my substrate are involved in this process. Both substrate and nucleophile are involved in the 1 step. So this is where people get confused. The 2 refers to the fact that it's bimolecular. Both molecules are involved, but is a 1-step process. SN2 reactions are always 1-step processes. So now what ends up happening is that I simply replace my leaving group with my new nucleophile. And all of the other stuff that we have said about, mechanisms is that we still just move electrons, arrow pushing has to make sense, and we still conserve charge. So now when I pop off this bromine, it is now going to be Br minus, because charges are still conserved. But this is it. This is essentially all that happens. Now, a couple of things just happened that we didn't discuss, but you guys may already know. What happened to my carbon center? Does it still have the same general shape, or did it kind of flip?
I guess it flipped, and I was gonna ask about that because I don't know, when I was like drawing it, I drew the arrow attacking like right where like the bromine is, so I was just gonna redraw it like exactly the same, but instead of saying bromine, it was just gonna say OH.
Well, here's the rub, is that this will invert. That is the fancy term. All right, and we're gonna talk about why that is right now. So do you have this? Can I erase so you guys look good?
Wait, just.
Oh yeah, no, take your time. I have nowhere to be tomorrow because I didn't teach today. I went to Maryland.
How was that?
Nice.
It was very nice. I went and saw the Naval Academy. You can't do tours right now because of COVID, but I went and saw it, and I went and got some crab and just sat by the water. Just sat in my car. It was raining today, so I just grabbed like seafood and just sat in my car and watched the water, and it was very peaceful. Then I came home and I fell asleep, and I realized that I had to take my garbage out because it smelled really bad, and my apartment smelled kind of bad. I don't remember what was in there. Had to be something bad. So
Probably food.
I'm assuming something, but I don't. Usually it's chicken, right? Or chicken's
Yeah.
usually what the culprit is, but it wasn't chicken because I haven't had chicken in a while, and I haven't thrown out any dairy in a while, so I don't know what it was, but it smelled bad, and I was like, I really hope it's not something else in my apartment. So I've been after taking a nap, I went through and just started cleaning stuff. I'm just like, hopefully tomorrow when I wake up, it'll smell better. That's the goal. You know, you ever have that where you have like a bad smell and it just kind of lingers, but like even though you clean everything up, it's still kind of there. Like you're psyching yourself out, like I can still smell it, but I'm hoping once I shower tomorrow, it'll be fine. But it's all right. So,
Yeah.
Going back to this, none of my old man nonsense. We have this inversion that's happening, and this inversion only happens in SN2, and we'll talk about why that is for SN1 later when we get to it. But this is what's happened. So I'm going to erase this now. If you guys are all good.
Yeah, I'm good.
Okay. So the reason why this happens, and I think this is why Melissa was asking this, and this is a really good idea, is that when our nucleophile comes in, right? And this is something that, do you guys remember when we learned about Vesper and valence bond? We learned about atomic orbital theory and kind of talked about MO theory and all that stuff. Do you remember that at all?
I kind of remember.
That's
Yeah.
okay. So when we talked about all this stuff, like the Lewis dot diagram shows us connectivity, but it's really bad at like showing us 3D. So that's where Vesper comes in. And Vesper is useful, but it doesn't account for like a lot of electron. Basically, you don't describe orbitals all that well. And orbitals are how bonds form, right? So then we started getting into atomic orbital theory, which had hybridization, which kind of accounted for how those things said. And then molecular orbital theory was like the fancier version of that. But the main thing here is that when we think about this type of chemistry, this is why the 3D shape is important, because when we form a new bond, we have to see where that bond is forming. So if you remember, when I am doing what is the hybridization of the carbon in all of these reactions that I just said it always has to be?
SP3.
SP3, right? It always has to be an SP3. So I know that you guys are super great chemists, and I know that you can. I'm going to draw our molecule, and I know that you guys are totally going to know this because you guys are totally with it, and you always paid attention to everything I said and every professor after me. He lied to himself.
I don't know about Paul. I don't think I ever paid attention to Paul.
So when we draw these lines represent the bonds, right? The actual bond formation, but we're not actually drawing the what? The orbitals, like we just talked about. We said that this was an sp3 hybridized carbon, which it is. And so now this is what our hybridization would look like if I actually drew it. From this carbon, you have this front big bulb coming out, and at the back side, you have this very small. So if I was to drop down here like this is what an sp3 hybridized orbital looks like. You've got the big, larger part, that's the bonding side, and then you have the small part, which is the anti-bonding side. So where must electrons always reside? They must always reside in the orbitals. They can't exist out of them, right? Well, let me rephrase that. Where are they always found? They're found most likely in the orbitals. I forgot. You guys know probability. It's a probability. They're most likely found in the orbitals. But this orbital overlap is where we're going to have bonds form. For anyone watching online later, I forgot that probability is a thing for a second. I apologize. That's more of a quantum reality. But in order for the new bond to form, where do you think these electrons have to go? The back one or the front one?
The front one?
No, the front one's currently occupied.
Oh.
The back one, because that is unoccupied. This is why we call it backside attack. It attacks the backside of the orbital. It is now going to go into that empty space. It's free real estate. And so now what ends up happening is that we get something called a transition state. Transition states always happen in every reaction you can think of. The easiest way to think of a transition state is it is when your reaction is still in process, but it is not quite the starting material, it is not quite the product, it is 50-50 mix. So at this point, right before the arrow attacks, how much of the bond is existing between the carbon and the bromine? It's 100%, right? This bond is 100% in existence. Over here, this is 0% in existence because the bond hasn't started forming yet, all right? When we get to the product at the end, those will flip, right? The bromine will now be 0% because the bromine has left, it's our leaving group, but now our OH will have formed 100%. But in the transition state, and this is where we use this funky little thing here, our carbon undergoes this inversion. Actually, I need to restart it. That's not going into the page. That is just showing that it is actually, that's a, I should do that. I should do this one. So in the transition state, like I said, you're not quite to the product and you're not quite to the, and you're not quite the reactant still. So what percentage are these bonds, do you think then?
50.
Then 50-50. So this bond is 50% formed, our nucleophile on our substrate, and this bond is 50% broken. So you can see, and I'll turn on my camera for this, and I realize the camera's not on, is that when my nucleophile attacks like this, at the transition state, my carbon is now completely linear, right? Those hydrogens are all going straight up and down like that. Does that make sense? So nucleophile attacks, transition state, leaving group is coming out the back. I am halfway formed this bond and I've halfway broken this bond. Now that transition is going to keep going and eventually my leaving group will leave. So I have to invert because I attack from the backside. It forces that bond to shift over. Does that make sense? So when I am doing this to methyl bromide, there's no real cause to it. Nothing has changed because this doesn't have stereochemistry. Because I have 3 hydrogens, they're all the same. No big deal. But when I have a stereo center now, what is going to always happen to my stereo center? If a stereo center is present, it will always invert. Meaning, if I, like we were talking at the beginning, Max, if I said I have a 2s2 bromobutane and I did a SN2 reaction, whatever my nucleophile is, right, provided I still have a stereo center at the end, it's now going to be 2R. So I'll always invert a stereo center from S to R or R to S when I do SN2, provided it was a stereo center and it is still a stereo center. Does that make sense?
Yes.
Okay.
So if you had like a dash and you have an SN2 reaction, the dash is gonna, or the wedge is gonna change to the dash after?
Yeah, that's one way you can think about drawing it. So the way I drew it here is just that if I was to draw the final product, it would look like this. I'm sorry, I'm tight on space. So you can see that since my nucleophile is in plane, it's just changing direction, right? So before my leaving group was pointing to the right when it was bromine, now it's pointing to the left with hydroxide. So that's just it. But yes, and we will do an example of that when we do a practice problem. So can I erase this or you guys still writing down?
I'm good.
Oh, this is my symbol for transition state. It's a double T cross. And so that is this. So if you're a professor, this is a very common question is, what is the transition state? And then you would just draw, you have half of this bond form, half of this one broken, and then it's that linear, your carbon here, your substrate, your electrophile, this hybridization is kind of going, it's right in the middle as it's inverting. So Okay, so now let us put this into practice. I'm going to grab a drink and throw my clothes into the dryer. But my dryer's not right there. I don't have to go downstairs because I have one in my apartment. I'm going to draw 2 reactions, and I want you to draw me the products of those reactions. Don't worry about the mechanism for right now. Just try to get the products. If stereochemistry matters, then include it. Put it back. Okay, so what's the first thing that you should check out for a reaction?
sp3.
Yep, you want to make sure that your carbon in with our leaving group, which is called our what? Starts with E.
Electrophile.
Our electrophilic carbon, yep, is an sp3. So sp3, check. sp3, check. I have a leaving group of bromine, leaving group of chlorine. Those are good. And that entire thing is called the substrate. So far, so good. Now, over our arrow, and this is how you write reaction nomenclature, right? Is you essentially just have what is being involved. So the key mistake that a lot of people make is that they see NaOH, sodium hydroxide, and they think, well, this is neutral. What's the point? But don't forget, this is Na plus and OH minus. And it's very important to remember this because whenever you see a metal first, sodium, potassium, lithium, whatever it may be, those are always positively charged. So that means that on the other side, it's going to be a negative charge. So here, sodium, positively charged, and then CN, cyanide, negatively charged. All right, so whenever you see a metal like that, don't forget that there is a charge there. Why is the metal there?
To make it a base?
Nope. Is the metal actually participating in the reaction?
No, it's a spectator ion.
All it is just to stabilize the charge, right? If you have negative charges and you have positive charges, it just stabilizes it. That's all it does. And this is, just the process of how you make stuff. But this is it, is that now we have this wonderful thing here. So all that's going to happen is that when we do these reactions, as Max said, is that we simply just draw the opposite wedge or dash like that. So now where it was chlorine on a wedge, now it is OH on a dash. And the same thing here. But which one of these is correct? That I'm going to draw at the bottom. Which one of these is correct?
The one with the.
Oh, sorry.
dash?
Sorry. Which one of those is correct? I apologize for making that much worse than it had to be.
Is it a 50-50 one again?
Well, this is an SN2, and SN2 should always give you 100%.
Okay.
The dash.
They're the same thing.
Oh.
Because is this center a stereo center? Nope, not a stereo center. Because you have the same thing on the left side as you do on the right.
Right.
So this is the trick. This is where chemistry likes to mess with you, right? It always likes to bring back stuff that you have covered before, right? So always watch out for this. This is a good question that professors like to throw at you to make sure you're paying attention to the, this is the stereo center or whatnot. So
can you draw the arrows just to make sure I did it right?
yep, I can do that. So, but I'll get on this. Can I erase this?
Yeah.
Okay. All right, so in this reaction, in our first one, we had this, right? Our BR or CL or BR here or something.
CL, but.
Right, so our OH is our nucleophile, and our nucleophile is electron rich. Since it's electron rich, that's where the, so this is going to come from the backside. It's really hard to draw here, but it's going to come from the backside of that chlorine, and that chlorine is going to pop off like that. And so then that's why you're going to end up with this. Does that make sense? Okay, and that's really what's happening, is that we're just, so if you were, our chlorine is like this facing you, so if you turn it around like that from the side, your nucleophile will attach that way and that pops off. Is that what you had for your arrow?
Yeah.
Yep, and it would look the same way for the other one. Okay, so this is the important thing now. We have now defined SN2. We have defined substrate, nucleophile, leaving group, and electrophile, right? And so what's really at the heart of these questions is you have those four reactions, SN1, SN2, E1, E2. How do I know which one's going to happen, right? So there are a few things that we can use to help us out. So the first thing you should always look at is the substitution of your carbon. Meaning, is it a methyl carbon? Is it a primary? Is it a secondary? Is it a tertiary? So for example, what type of carbon is this? If this is my electrophile and I have my nucleophile coming in. What type of, is that a methyl, a primary, secondary, or tertiary?
Secondary.
Nope. How many carbons is that carbon attached to?
One.
A primary.
It's a primary, right? What about this? That should all come to the same point. I'm just really bad drawing. Is it attached to any carbons?
No.
It's a methyl. So if you're attached to no carbons, that's a methyl. And then finally, just to make sure we'll do the other two. Which one is this? What type of carbon is this? Was that a methyl, primary, secondary, or tertiary?
Tertiary.
Yep, because you are attached to 1, 2, 3 carbons, right? So it's a tertiary. So this is why you always look at the substitution of your carbon, because this is the most important thing. First off, is it sp3? If you meet that requirement, then you continue on to the next thing. Which of these do you think happens quickest? So I'm going to draw this again, and this is a very important thing to make sure you guys understand. When I did this example earlier, right, and I showed you how the actual orbitals are involved, right? Oh. This, right? We said that this was the bonding orbital here, and then this was the anti-bonding orbital. So the electrons that were actually doing the attack had to come from which direction? Front side or back side?
Backside.
Backside, right? So it has to come in here and attack like this. But how small is that anti-bonding orbital? That backside orbital? It's pretty small, right? So what is going to rear its ugly head? What's around it right now? There are hydrogens. Are hydrogens big or small?
Small.
Small. What happens though if I start replacing hydrogens with methyl groups? Is it more crowded in there now, or is it less crowded?
More
Crowded.
It's more crowded in there. And so then what's happening to that space that I can come in and attack now?
I mean, it's being reduced.
It's harder to get in there, right? And so what we find is SN2's biggest limitation, steric hindrance. This is what will limit whether or not an SN2 reaction can happen. So based on what we just showed you, methyl, primary, secondary, or tertiary, which one do you think SN2 happens to the quickest?
Methyl.
the methyl.
Methyl. Your methyl will always, always, always be your fastest. So I'm going to erase this. Your methyl is always going to be your fastest. And it'll be faster than primary, and it'll be faster than secondary, and it is much, much, much faster than tertiary. And we say that it is so unlikely to happen that SN2 will not occur for a tertiary carbon. So if you get drawn something that's a tertiary carbon, you can automatically say it can't be an SN2 reaction. Does that make sense? So steric hindrance is always your enemy when you're dealing with substitution. The way that my professor explained this to me, and my professor was insane that taught me chemistry, and I think I've mentioned this before. I'm really normal and sane compared to the guy that taught me organic. And I want you guys just to sit on that thought for a second and think about someone much weirder than me teaching organic. But the way he explained it to me,
I think you're weird.
The weird stuff I did in class, like the bucket of grades or, name calling or ranking you guys by stuff, he did so much worse stuff than I ever did. But the way he explained this in class has always stuck with me. So imagine, Mags, you're out and you're at a house party for some reason. I don't know if you go to house parties or not, but say you're at a house party and you're at a kickback and you look over and you see a cute person across the room, right? For whatever reason, right? You see a cute person across the room. Now, you're like, wow, that is an attractive person. And I actually want to talk to them because they are that attractive, Same goes for all of you guys. Imagine you're all in this scenario. Now, is it easier for you to go talk to that person if they're by themselves or if they're a group of friends?
By themselves.
By themselves. That's how you should always think of SN2. If that carbon is chilling by itself with one of its carbon friends, always is going to happen a lot easier. It's quicker. If it starts bringing its carbon bitches along with it, then who knows what's going to happen. It's going to be a lot tougher. But this is the idea. It's just that you cannot have that. Steric hindrance is always what's going to delay you. All right. So that is the first thing that we need to know. So now you know that steric hindrance, methyl carbon, primary carbon, secondary carbon, will not happen for a tertiary carbon whatsoever. All right. Now we also want to talk about a couple of other things. So something else that matters is the strength of our nucleophile. So I'm going to draw 3 common nucleophiles, and I'm going to ask you a question. So we could have OH minus, CN minus, and we'll say N3 minus. So real quick, looking at these very common nucleophiles for SN2 reactions, do you think nucleophiles need to be strong or weak?
Strong.
Strong.
For SN2 reactions, your nucleophiles must be strong. Must be strong. And the reason why is that they are attacking something that has a leaving group. It has to be able to attack and pop off that leaving group. So it has to be very nucleophilic. So if you have a weak nucleophile, that's going to be the case. So as I said before, an easy way to identify a strong nucleophile is typically a negative charge. It's not always true. There are one or two exceptions. But for example, which one would you say is the stronger nucleophile, hydroxide or water?
Hydroxide.
Hydroxide. So if you have two things, right, that one is nucleophilic, one is a strong, one's a weak. If you have the negative version of something, like you lose a hydrogen, a proton, then that's always going to be the strong one. So this is strong. And this is weak. So we know that you need to have an sp3 carbon. It needs to be methyl primary secondary, and you need to have a strong nucleophile. All right. Now there's just one last thing that we need to introduce. Any idea?
Base.
Those are for elimination reactions. But for the SN2 reactions, we need to care about something called solvent. And I need to grab my phone real quick. So solvent matters because when we run reactions, they run in solvent because we mix them and there's a better chance for molecular collision. If you remember your molecular collision theory, because I know you guys, that's all you talk about when I'm not around, is you guys talk about that. But this is the idea, is that we have molecular collisions and they happen better in solvent. So we always run reactions. Not all reactions anymore. We are past that. But solvent is going to matter. And the reason why is that I want to take a look and see if you guys can figure out. So imagine I have, this is my nucleophile, right? And then I have a nice bromomethyl, methylbromine as my, ooh, that's really bad. Try that again, sorry. You know what, that'll do, whatever. So now I'm doing this reaction, right? So I'm going to give you two solvents, and I want you to tell me which solvent do you think is going to be better for the reaction to occur. And you can use your best judgment. So solvent A is going to be acetone. This is what the stuff you use in lab to clean your glassware and stuff. It's also a nail polish remover. Your other solvent choice is water. So I want you guys to sit and think about which of these is going to be the better solvent. So when I say solvent, remember, there's going to be like a lot more solvent molecules than there are going to be the actual reaction molecules. So you have solvent option A and solvent option B. Think about that for a few seconds and think to yourself, which one of these is going to be the best solvent? Meaning, which solvent is going to help facilitate the reaction, right? You always want stuff that is always going to help the reaction going forward. Okay, so the reason why I took a pause there is that the 10 minutes is the 40 minutes is about up. So think about this. I'm going to reopen it in like 10 seconds, and then we will discuss what the answer is going to be. Just think about why. Pick an answer, but try to give me a reason why. Now, you may already know because you guys are really smart, and you've also been talking about this for like 2 weeks. I haven't seen you guys in a while, so you guys already may have an idea. But I'll be right back.